Dry ice is a special kind of ice that does not melt into water, but creates a thick white fog when it touches it. It is so cold that it can freeze a strawberry in just a few seconds or keep vaccines preserved for several weeks. But unlike the regular ice we use at home, dry ice is not made from water. It comes from carbon dioxide, the same gas that human beings release when they breathe out. When this gas is cooled and compressed until it becomes solid, it turns into a white material that looks just like regular ice. The main difference is that dry ice never turns into liquid. When it warms up, it changes directly from solid to gas, a process called sublimation. That is why it simply disappears into the air, leaving no puddles or moisture behind. Because it does not leave any water when it evaporates, dry ice is perfect for preserving food and medicine. Its mysterious fog is also used in theaters, concerts, and movies to create visual effects. And its physical properties are so unique that it is also used for industrial cleaning, without the need for chemicals. But how exactly is this incredible material made on an industrial scale? Let us discover, step by step, how dry ice is produced, from gas to the solid blocks that keep the modern world cool. Dry ice was discovered by accident in the year 1835 by the French chemist Adrien Tillorier. While studying liquid carbon dioxide inside a high-pressure cylinder, he noticed that when he opened it, part of the gas escaped, and what was left turned into a cold, white mass. That was the birth of dry ice. Even though it was discovered in the 19th century, it took nearly 100 years before it became useful in practice. In the 1920s, American chemical companies began producing and selling dry ice commercially. At that time, it was mainly used to keep food cold during transportation, especially meat and dairy products, because it stayed frozen without melting into water like regular ice. During the Second World War, dry ice became even more important. It was used to preserve food, medicine, and vaccines for soldiers overseas. While ordinary ice melted into water, dry ice simply evaporated into gas, keeping everything cold and dry. With a temperature of about 78 degrees below 0 Celsius, or 109 degrees below 0 Fahrenheit, dry ice is one of the coldest materials used in industry. It is essential in places where there are no refrigerators or electric cooling systems. For example, it is used to transport organs for transplants, such as hearts, which must remain frozen until they reach another hospital. It is also used to transport vaccines, biological samples, and other sensitive materials that must stay cold. And when dry ice is dropped into hot water, it releases carbon dioxide gas rapidly, creating that thick, magical fog often seen on stage or in films. But before that can happen, everything begins with the production of pure carbon dioxide, the main ingredient of dry ice. In the United States, this gas comes from several industrial sources. In breweries and distilleries, carbon dioxide appears as a byproduct of sugar fermentation during alcohol production. The gas is captured, purified, and stored for later use. It is also produced in ammonia and fertilizer plants, where carbon dioxide is collected before being released into the air. Refineries and chemical plants generate it while turning crude oil into fuels. And in some power plants, carbon dioxide is recovered from the burning of fossil fuels. Before it can be used, the gas needs to be purified. It goes through filters that remove dust and solid particles, and then through washing systems that eliminate other unwanted chemicals. Only after that is it ready to be turned into dry ice. The gas is then compressed under high pressure and cooled to temperatures between 20 degrees below 0 Celsius and 30 degrees below 0 Celsius, which equals between 4 degrees below 0 Fahrenheit and 22 degrees below 0 Fahrenheit. Under these conditions, carbon dioxide becomes a clear liquid, much easier to transport and store inside stainless steel tanks. These tanks, known as cryogenic tanks, are designed to handle high pressure and extreme cold. They are equipped with safety valves and are kept cold at all times to prevent evaporation. Some can hold thousands of tons of liquid carbon dioxide. From there, the liquid flows through pipes to the machines that produce the solid dry ice. Inside these machines, the liquid carbon dioxide goes through a rapid reduction in pressure. When this happens, the liquid instantly turns into a mixture of gas and small solid particles, what is known as carbon snow. This transformation occurs because, during expansion, the gas absorbs heat from its surroundings, becoming even colder. Part of the carbon dioxide turns back into gas and is released through ventilation. The solid part, the snow, collects inside a chamber in the machine, forming a fine, powdery frost that looks just like real snow. This carbon snow is then pressed under high pressure to form solid blocks of dry ice. Large hydraulic pistons compress the material with immense force, creating dense, compact blocks at 78 degrees below 0 Celsius or 109 degrees below 0 Fahrenheit. After pressing, the blocks are cut into different sizes depending on how they will be used. In addition to these large blocks, dry ice is also produced in small cylindrical shapes called pellets, usually between 3 millimeters and 16 millimeters wide. They are made in machines called extruders, where the snow is pushed through holes with great force. The larger pellets are used for cooling and transportation, while the smaller ones are used for dry ice blasting, a cleaning method that uses frozen air instead of chemicals. These pellets are so cold that when they touch metal surfaces, they remove dirt, grease, and paint without damaging the material. That is why they are widely used in airplane factories, electronics companies, and plastic molding plants. It is an efficient and environmentally friendly way to clean machines using nothing but frozen gas. After pressing, dry ice remains extremely cold and must be stored carefully to prevent it from evaporating too soon. Because carbon dioxide is valuable and cannot be wasted, factories recover and reuse the excess gas that escapes during production. Nothing is lost. What returns to the air is captured again, creating a cycle of efficiency and sustainability. The finished blocks and pellets move along conveyor belts to the testing and packaging area. There, each piece is checked for weight, size, density, and purity to make sure it meets quality standards. Once approved, the products are packaged and prepared for delivery. The biggest challenge with dry ice is storing and transporting it before it disappears. Since it constantly changes from solid to gas, it must be kept in thermal boxes made of thick polystyrene or polyurethane, which act as natural refrigerators. These containers help reduce the daily loss, which is usually between 5% and 10% of the total weight, depending on the outside temperature. Thanks to this careful packaging, dry ice can be shipped safely to clients all over the world. During transportation, dry ice keeps cargo cold for several days. Trucks, airplanes, and cargo ships depend on it to preserve meat, seafood, medical supplies, and even flowers. In the United States, large distribution centers in Illinois, Texas, and Georgia supply hospitals, laboratories, and industries across the country. At 78 degrees below 0 Celsius, or 109 degrees below 0 Fahrenheit, dry ice stays cold entirely on its own. It does not require electricity to remain frozen. In the food industry, it ensures that products arrive frozen and fresh. In hospitals, it preserves vaccines, biological samples, and organs for transplant. In factories, it is used for deep cleaning. And in entertainment, it creates the magical fog that fascinates audiences in concerts, theaters, and films. Dry ice is also used in scientific research. Laboratories use it to create ultra-cold environments for experiments or to freeze materials quickly without contamination. It is